चलिए स्टार्ट कर लेते हैं ये रिवर्स में स्टार्ट करें इससे W16QP23 ठीक है. So we're going to start with the last question. एक सेकंड जरा ये इसको बंद कर दो. अच्छा, so we're going to start with the last question first. So the question is this one. Okay, a sequence of reactions is shown starting with the alcohol C3H7OH, and फिर is saying skeletal formula of the alcohol. It has to be. अच्छा, that's got to be drawn. थोड़ा सा slow over system, just a second. अच्छा, so the skeletal formula of the alcohol C3H7OH that needs to be drawn. So that part is kind of easy. ठीक है कि प्रोपेनॉल का वो कह रहा है. Just wait 1 second. So propanol is now the issue is okay, the only thing that's given to you is okay, you're not told. Just give me 1 second. Achha, so the only thing that's not been told is this propan 1-ol or propan 2-ol? This one over here, this molecule over here, is definitely going to be propan 1-ol. Okay, the OH is going to be right at the end. Okay, so the OH is going to be right at the end. The way we figured that out is okay, it's turning into an aldehyde. The aldehyde is right at the end, so that means the OH would be right at the end. And you have to draw the skeletal formula. So it's 3 carbon atoms. That's one. That's the second one, and that's the third one. So the OH, that's your 3 carbon atoms, and the OH is going to be on the third one. Okay, so you've got your OH group on the third carbon atom. That's and it's going to be propan 1-ol because it's forming an aldehyde, and on the other side it's forming a carboxylic acid. The end पे change आ रहा है, so that means the OH must be right at the end. State the reagents and conditions needed for reaction 1 and also for reaction number 2 as well. Now this is oxidation. A primary alcohol turns into an aldehyde and then it turns into a carboxylic acid. So in both cases, the reagent is K2Cr2O7, potassium dichromate 6 in both cases. अच्छा, लेकिन what were the difference in conditions? Any idea when do you get an aldehyde and when do you get a carboxylic acid?
For carboxylic acid, we have to heat under reflux.
Again, for aldehyde?
Distillation.
Okay, so that's the main difference. Okay, the reagent is going to be exactly the same. You do distillation because as aldehydes don't form hydrogen bonds and they evaporate very quickly. So as soon as aldehydes are formed, you quickly remove it by distillation. So the conditions over here, it's going to be distillation. And for the other one, it's going to be reflux. When you reflux things they can't come out of the container because there's a condenser on top that's blocking any vapor that's evaporating. So state the reagents and conditions. We've already done that. And name P the organic product of reaction number 3. So that would be, that is going to be an ester. Okay, you're going to have, 1 second. Achha, so just 1 second. So this one, P, propanol and propanoic acid. That's easy. You can draw propanol and propanoic acid. They would form an ester. So it's going to be an alcohol, and it's going to be propanoic acid, which is going to be double bond O and OH. So how is an ester formed? An ester is formed that the H from the carboxylic alcohol and the OH from the carboxylic acid, they are lost. And when they are lost, the middle में an ester link is formed. The water molecule, it's a condensation reaction. So the water molecule is removed. And in the middle, they're gonna connect together and they would form an ester link. And you can add in the H's. So they're not asking for the structure in this case. What they're asking for is this carbon will have two H's, this one will have two H's, this one will have two H's as well, and this end one will have three H's. So what is the name of this organic compound?
Propyl propanoate.
Okay, so both sides it's 3 carbon atoms. This side it's prop, and the other side is also prop. Or double bond O side is known as O8, and this side is vinyl propyl. So it's going to be propyl propanoate. So this question is done. So we're going to move to the next one in the reverse order. As the next one is again about organic. So starting with this part. Okay, they have an alkene and you're supposed to name this alkene. So what is the name of this alkene? That's 1, 2, 3. I mean, let me just draw a slightly displayed formula of this. It's 1, 2, 3 carbon atoms. And on the third one, there's a carbon branch, a methyl branch. Then you have another carbon atom, and that one has a double bond. And after that, you have 2 more carbon atoms. That's another carbon atom and then another carbon atom. So what is the main chain first? What would you call the main chain?
Hex-2-ene.
So that's going to be hex-2-ene. Which side would you count from? Right side or left side? I mean, it's going to be the double bond has greater precedence. So you're going to try and give the double bond. It's hex-2-ene, right?
Yes.
Tanya, that's fine. What about the branch? You've got a branch as well. At what position?
4 methyl.
Okay, so it's going to be 4 methyl. So this is going to be 4 methyl hex-2-ene. And remember precedence, TK, make sure you remember the precedence order. Numbering is always done to give a smaller number to the most important group. Define the term stereoisomer. So what is the definition? Anyone, what's the definition of a stereoisomer? What's same?
Has the same molecular formula and
So that's fine. It has the same molecular formula. And what else is same?
Different structure.
Different structure.
no,
Nahi.
I think it's same structure, structural formula.
So they have the same molecular formula. They also have the same structural formula as well.
Yes, and but are arranged in different arranged in different ways.
Yeah. So basically they have. Yes,
Something.
exactly. So basically they have a 3 different.
The atoms arranged are in a different order.
Not in order, different 3-dimensional representation or 3-dimensional orientation of the bonds. They have the same molecular formula, same structural formula, same structural. I mean, when I say the same structural formula, that means the atom bonding is exactly the same. But what is different is a different 3-dimensional arrangement of the bonds. Arrangement of bonds. Okay, so make sure you remember this definition that even the structural formula is same when you have a stereoisomer. For example, optical isomers, like your two hands. Your two hands are exactly, they have the same structural formula. The thumb and the fingers, etc., are in the same order, but the three-dimensional orientation is different. State and explain how many stereoisomers of this structure there are. So how many stereoisomers does this have? I mean, this molecule over here in total.
4.
Okay, so it's going to have 4. And what are those 4 isomers? I mean, that's fine. It's got 4 stereoisomers, but what are they?
2 cis-trans and 2 optical.
Okay, so you've got a cis-trans because a cis-trans would be around this double bond because if I add in the H atoms, for cis-trans, the condition is that around the double bond, the carbon must be bonded to 2 different groups, and this carbon is also bonded to 2 different groups. And remember, structural formulas are not 3-dimensional representations. So this is not the 3-dimensional representation. They might ask you for the 3-dimensional representation, but at least this is not the 3-dimensional representation. So you've got geometric isomers. Number 1, you've got geometric isomers around isomers cis and trans. Around the serial bond C. And the other one is, do you have optical isomers over here? And which carbon atom do you have optical isomers? I mean, which one of them is forming optical isomers? I mean, which carbon in this is making, out of all of this, is making optical isomers?
Carbon number 4.
Okay, so carbon number 4 over here. You've got a chiral carbon, which is why you also have. So which is why you also have your mirror images, non-superimposable mirror images. You've got 2 optical isomers that are known as enantiomers. So my board for some
Sir,
reason.
can I ask you a question?
Yes.
Sir, can you tell me ये कौन सी year का paper है?
अच्छा ये वाला, this is W16 question paper 2-3 है, ठीक है?
Okay, sir, thank you.
W16 question paper 2-3. Chale, next, I said, remember, and you also have to explain this. I mean, it's a 4-mark question, so you must have, I mean, you have to add a certain point over here that when you have geometric isomers, when you have a double bond, and each carbon is bonded to 2 different groups. When you have a chiral carbon atom, because there's a carbon atom that is bonded to 4 different groups, which is this one. Whenever you have a H नहीं बना हुआ यहाँ पे, you can add in the H atom. So if you add in the H atom, so this one is bonded to 4 different groups. All 4 sides are different. So you have to give some brief description of what this is, and that will get you 4 marks. Now you have to name this molecule. It's a double bond, and so there's a carbon double bonded with another carbon atom in the middle, and on the right side there are 2 CH3s, and over here you also have, as you also have 2 CH3s, and on this side you will again have 2 CH3s. So what's the name of this molecule?
Butene comes at the end, and 2,3-methyl dimethyl.
So the main chain, the longest possible chain, that's 4 carbon atoms. That's a butene. That's your main chain, because you got a double bond. This is first carbon atom, second, third, and a fourth. And there's a methyl branch on the second and the third. So it's going to be, I mean, the prefix or the branches are going to be 2,3-dimethyl and butene. And draw the skeletal formula of the organic product of the reaction of this compound with cold dilute acidified. Now that is mild oxidation. What happens when you have a double bond and it undergoes mild oxidation? What does it turn into?
Diols,
So,
which are alcohols.
okay, so the double bond will go away and you'll have OH groups in its position. Everything else would remain there, except the double bond in the middle would be gone. So mild oxidation results in the formation of diols and the skeletal formula. So that's 4 carbon atoms in a line. That's 1, 2, 3, 4. So that's 4 carbon atoms in a line. And then there's a carbon atom on the second and the third. And in the middle, there's going to be OH groups. So you can add an OH group here, and you can add an OH group over here. The middle 2 carbon atoms will have these extra OH groups, and you show OH groups in the skeletal formula. So that's 1, 2, 3, 4. 1, 2, 3, and 4. Second one and the third one, there's a carbon atom. And name the organic product of the reaction of this compound with hot concentrated. What happens when you have strong oxidation? What happens to this double bond over here? It's hot concentrated KMnO4.
Ketones are formed?
Propanol.
It won't be, it's going to be ketones probably. So let me just quickly revise what happens when you have strong oxidation. That this is the part for strong oxidation. When you have alkenes and you undergo hot concentrated KMnO4 oxidation, strong oxidation, the double bond breaks completely. And the 2 pieces that you get, if you have 2 carbon chains on it, it will turn into that particular double bonded carbon atom will turn into a ketone. So if I go back, this molecule over here, the double bond is going to break, and you focus on this carbon atom. It's got 2 carbon chains attached to it. So this has 2 carbon chains. So if the carbon that was making the double bond had the fragment that is going to be obtained has 2 carbon chains, then that will turn into a ketone. The other side is exactly identical. That's the same thing would happen to this other carbon atom. The double bond would break completely. So make sure you remember this, that that strong oxidation of alkenes, if the double bond breaks completely 2 carbon chains, it turns into a ketone. That particular carbon turns into a ketone. If it had 1 carbon chain, that particular carbon atom which was making the double bond will turn into a carboxylic acid. If it had no carbon chains, it would turn into a carbon dioxide and H2O molecule. So what is the name of this thing? What ketone is this?
Propanol.
Okay, so that is propanone. Next one is draw the structure part of a molecule of the addition polymer formed from this compound, this compound, he's talking about this one. So how do you, and 3 repeat units. So how do you draw a polymer? The double bonds, they react together in addition polymerization. And when they react together, they link up with each other. It's like an addition reaction, and you have to draw 3 repeat units. So we're going to draw another one. And the molecules would link up. Make sure you draw continuation bonds. The double bonds in the middle would turn into single bonds. And that's, that's about it. Since they're asking for 3 repeat units, so you're going to draw 3 repeat units, but the other way of doing this was just draw one of them and write N next to it. TK, is that clear? Now,
Yes, sir.
So now the next one is you've got this molecule and you have to name this. So it's what is it? It's carbon, double bond, carbon with 2 H's. And on this side, there are 2 CH3s. So how would you name this? What's the name of this molecule?
2-methyl propene.
Okay, so the longest chain, remember the longest chain must contain, it should have the double bond in it. So it is a propene, and there's a methyl on the second one. So it's 2-methyl. Propene. And he's asking for the reaction of this alkene with HBr. So this is, I mean, this is just an electrophilic addition reaction mechanism that you have to draw, and you have to draw every single curly arrow partial positive. So yahan pe over here, electrophilic addition. Remember, all alkenes undergo electrophilic addition reaction. So this is the mechanism that they're looking for. Okay, you add a double bond. The molecule was already polar, so I'm going to do the working over there. A carbocation is going to be formed as an intermediate. So H over here is positive and Br is partial negative. This molecule is already polar. The positive H is going to attract electrons from the double bond. And the electrons over here are going to repel the electrons in this bond over here. So these electrons are going to be repelled. Next step is, the next step is that so the next step is that the positive H is going to attract the electrons from the double bond, and it's going to bond with one of the carbon atoms. And a carbocation would be formed because the double bonded electrons over here will be taken up by the positive H, and it will bond with one of the carbon atoms, and because the double bonded electrons are gone, so this carbon gets a positive charge. Br, on the other hand, will then come back. It got repelled first, but now it's going to come back. It's going to join up. So that's it. And that's the mechanism. So the reason I drew the H over here is because, I mean, they were attaching the Br on this carbon atom. Is this the major product or the minor product?
This is the major product.
Okay, so the Markovnikov's rule is that the H atom from HBr would always like to bond with the carbon that's already bonded to more H atoms. So over here, it's bonded to 2 H atoms. That particular carbon atom is at least directly not bonded to any H atom. So the major product is going to be this one. And I think in the next part, he's saying explain fully why 2-bromomethylpropane is the major product, while only relatively small amounts of 1-bromo. So it all depends on this carbocation. You've got a stable carbocation and you've got an unstable. The one that we have drawn above, this one, I'm just copying the one above. That is a stable carbocation. The other one that is possible is the other one that you had a double bond over here, and the H instead bonded with this carbon atom. And so you had a double bond over here and the H came and bonded with this carbon atom. Now that's a 3-degree carbocation. And this one, why do I call it a 3-degree carbocation? Because the carbon is bonded to 3 carbon chains. It's in the middle of the carbon chains. There's a carbon chain on top, right side, left side, everywhere. This one over here is a 2-degree carbocation because it is right at the end of the chain. It's got 2 hydrogens. There's only 1 carbon chain that's attached to it. So this one is a 1-degree carbocation. Now, a 3-degree carbocation tends to be stable. The 1-degree carbocation tends to be very, very unstable. What's the reason for that? This one has, I mean, basically all you have to write is it's got more electron donating alkyl chains. Which decreases carbocation charge density. I mean, that's the standard explanation you're going to write, that a 3-degree carbocation is going to be more stable. And that's the wording that you're going to use. But the explanation for this is, whenever you have a carbocation that's in the middle of large groups, it's CH3 over here, CH3 over here, CH3 over here. Carbon chains tend to have an electron donating effect. So the positive charge is going to be really, really It's going to be really, really small. Over here, the carbon is not surrounded by large groups. I mean, there's a carbon on this side, but hydrogens don't have any electrons. They don't have any spare electrons. So carbon is not surrounded by large groups. So when it becomes positively charged, it has, I mean, the positive charge has no electrons surrounding it. So relatively speaking, the positive charge is much bigger in size. Is that idea clear? That think of yourself in the having a positive charge sitting right in the middle of lots of electrons. Like there's 9 electrons over here, 9 over here, 9 over here. So you're surrounded by at least 27 electrons. The carbon has 6, hydrogen has 3. So 9 over here, 9 over here, 9 over here. So if you're surrounded by 27 electrons, obviously you're going to attract those electrons and the positive charge would become very, very small. So why is this more stable? The reason, or we can talk about this one. Why is this so unstable? It's so unstable. The reason is that the positive charge tends to be so large that the H that was trying to steal electrons from the double bond will not be able to do that. The electrons will be pulled back and the double bond will be reformed. Double bond वापस आ जाएगा because you got a very strong positive charge on the carbocation. So why would the H, it would be very hard for the H atom, the positive H atom that was coming from HPR. It would be very hard for it to pull the electrons from the double bond and bond with this carbon atom, because that carbon will pull those electrons back. So it would be very hard to actually form that carbocation to begin with. Is that idea clear? Why 1 degree carbocations tend to be very unstable and very hard to form. Is that clear?
Yes, sir.
And just to show this, that here's how the reaction was happening. You had a double bond. Initially, there was no positive charge, right? You had an alkene. The positive charge was on this one. The carbon tried to steal those electrons from the double bond. So it managed to do that. The carbon from HPR. And this carbon became positively charged. But the positive charge was so large that it will pull that electron back to reform the double bond. It's not going to get formed. It's very hard to form a 1 degree carbocation. This one is easy to form because if the H pulls the electrons from the double bond, steals those electrons from the double bond over here, the carbon can get electrons from elsewhere. There are 27 electrons surrounding it. So it doesn't really, it's not relying on that electron. So it will allow the H to take that electron because the positive charge would be very small anyways. So it's a lot easier to form. So that's the explanation. And these are the words that you're going to write. A 3 degree carbocation, whenever this is asked, a 3 degree carbocation tends to be stable. Why? Because it has more electron donating alkyl chains, which decrease carbocation charge density. That's it. No other stories need to be written. Okay. Is that clear?
Yes, sir.
So next one. So this question is over. We're going to move to the previous one. This one is, so this one is about explain why both lines show a steady increase in the values of the radii down the group. So the atomic radius is, I mean, one of them is, I mean, what are the two things? One of them is probably an ionic radius. So the graph below shows the radius values of the atoms and 2 plus signs, yes. So which line belongs to the radius of the atoms and which line belongs to the radius of the ions? I mean, which one is the radius of the atom and which one is the radius of the ion?
Dotted one will be for atomic radii.
Okay, so that would be for the atomic radii, and this one is going to be for the ionic radius. Remember, positive ions, the ion tends to be smaller. Why? Because they lose their outer shell electrons. Like if you have an atom, like in the case of magnesium, so it's 2, 8. The ion is going to be smaller because it would lose its outer shell electrons. So explain why both lines show a steady increase, because you down the group, you have more shells. That's it. So down the group, you have more shells, which is why electrons are going to be further away from from the nucleus. And State explained which line represents the atomic radius and which represents the ionic radius. I mean, we already did that. And over here, the explanation you have to explain as well. So the explanation would be that ionic radius is smaller because atoms would lose electrons in the outer shell to form the ion, which is why they're going to be smaller. Now it's a group 2 salt. When L is heated strongly, a brown gas is observed and a white solid remains. The white solid dissolves in water to form a colorless solution of M hydroxide. Addition of sulfuric acid produces a white precipitate. Now about hydroxides and group 2 hydroxides, the top one is insoluble. MgOH2 is insoluble. The bottom one is soluble. So he's talking about a colorless solution of the metal hydroxide. So it's probably going to be the bottom one. Most likely it's going to be the bottom one. And the other one is that it forms a white precipitate with sulfuric acid. That's a test for sulfate. I mean, that's a test for barium ions actually. So that kind of confirms that you're dealing with barium ions because that's a test for identification. Make sure even if you're not doing P3, make sure you remember the salt analysis tests that you already did in O levels as well. So a test for barium ions was you add sulfate ions or sulfuric acid to it, and it forms a white precipitate. So what is this brown gas? Which gas has a
nitrogen dioxide?
Okay, that's NO2. So which substance gets heated and produces NO2?
Nitrate. It basically would be barium nitrate.
Okay, so it's going to be barium. The anion over here would be the anion usse pucha tha, so it would be nitrate. And identify the M and write an ionic equation for the formation of the white precipitate. So we did figure that out. It's barium. The ionic equation is that why do you get a white precipitate with sulfuric acid? Because barium ions and sulfate ions, if they're both in solution, this ion coming from sulfuric acid and barium hydroxide, that also dissolves. So in the solution, barium ions and sulfate ions would form an insoluble precipitate of barium sulfate, and both of them would be aqueous. As I give the formula of the salt L and use it to write an equation for the thermal decomposition of salt. I mean, we kind of did that. So what's the decomposition of barium nitrate? What would be produced?
Barium oxide, nitrogen dioxide, and oxygen.
Okay, so it's going to be NO2 plus O2, and it's going to be 2 NO2 and half O2. Now, next one is calcium carbonate and calcium hydroxide can both be used in agriculture to write an ionic equation for the neutralization of acid by each. So calcium hydroxide. Okay, it's going to neutralize H+1 in the soil. The OH ions and the H+1 would react to form water, and calcium ion would be left as a spectator ion. And I think it's going to be 2 water molecules. And the same with carbonate. Like you have calcium carbonate, you react it with H+1 in the soil. So carbonates react with acids to produce carbon dioxide and water, and calcium ions would be left as spectator ions. But it's obviously going to be a salt. Like if you have HCl, it's going to be calcium chloride. If it's H2SO4, it's probably going to be calcium sulfate. But he's asking you to write the ionic equation only and explain why calcium carbonate is a better choice in areas of high rainfall. For the purpose in areas of high rainfall, why is calcium carbonate a better choice? Especially in areas with rainfall.
Does calcium hydroxide dissolve and wash into rivers?
So it dissolves and makes and it would eventually make a river and soil alkaline, right?
Yeah, eutrophication.
Eutrophication doesn't happen because of calcium hydroxide. It happens due to fertilizers. Okay. and makes water bodies and soil alkaline. Okay, excess calcium hydroxide. Or vice versa, you can write the other one is insoluble. Or you can just write while the other one is insoluble. Give the formula of the magnesium containing product of these reactions with cold water and with steam. So what happens when magnesium reacts with cold water? What is produced? And with steam as well.
Magnesium oxide.
It's going to produce magnesium hydroxide plus H2. And with steam, it's going to produce magnesium oxide plus H2. Now remember this thing that a hydroxide, let's remember this thing that a hydroxide at high temperatures would decompose into an oxide. Is that clear? So with steam, it's obviously at higher temperatures. So the hydroxide would turn into an oxide. Is that clear?
Yes, sir.
So we're done with this question as well. So which one is this one? This one is I think about enthalpy change. What is meant by the term enthalpy change of combustion, and standard word is used. So it's exothermic or endothermic, energy released or absorbed?
Release.
Sir, it is.
Okay, so it's energy released when what happens?
And 1 mole of a compound reacts in excess oxygen.
Okay, so 1 mole of any substance, not just a compound, because
Okay.
a compound indicates that it's a combination of two things, right? It could just be it could just be a carbon atom. So 1 mole of a substance burns in, but a compound would still be right. I mean, they wouldn't cut marks for that.
Okay.
So burns in excess oxygen, and it's measured under, because they've used the word standard, so it's measured under standard conditions. And write the complete equation. So this has to be 1 mole, C2H5OH has to be 1 mole, and the states are very important. So it's going to completely react to produce carbon dioxide and H2O. And there's going to be 2 carbon dioxides, and there would be 3 water molecules, and there would be, I think, 3 oxygens. This is a liquid. Under standard conditions, oxygen is a gas, carbon dioxide is also a gas, and water is a liquid. This has to be kept as 1 mole. Now there's an experiment that is going on, and you're being asked to calculate the heat energy. How do you calculate heat energy? It's MC. It's MC delta T. So it's going to be, and remember the alcohol is burning and it's heating water. So you're measuring the temperature of water. So it's 100 grams of water. So the mass is going to be 100 grams. The enthalpy change for water is specific heat capacity of water is 4.18, and delta T is 16.3. Can you even calculate this? And give me 1 second. And try doing the next part as well. So sorry, did anyone calculate this?
6813.4, sir, for the first part.
That's 681.
6813.4.
3.4, and that's 6813.4 joules, right? But there's one thing wrong with this, and that is that you have to give it to the appropriate significant figures. which is going to, in this case, it's going to be because everything, your values are up till, some values are up to 2 significant figures, the other ones are at 3 significant figures. So make sure when you write answers, don't write, I mean, keep the most accurate answer on your calculator, but just make sure that when you write values, write it up till the appropriate significant figures. So I'm going to do (6,800 joules) because my answer cannot be more accurate. I said, nee, 1 second. I'm not actually using 0.23 grams over here. All my values are accurate up till 3 significant figures. So I'm going to code this as 6,810 joules. Just make sure when you state your answer, don't state the answer that's given on the calculator. Make sure it doesn't exceed the significant figures that you're using in your calculation. So for 1 mole of ethanol now, so this energy is for 0.23 grams of ethanol, which is how many moles? Mass divided by MR, what do you get? How many moles do you get?
Five times 10 to the power of -3.
So this is the energy that is calculated for 5 times 10 to the minus 3 moles, and that gives you 6,810 joules. So for 1 mole, use ratios and tell me what's the, and you have to divide by 1,000 at the end, because, so what do you get? It's going to be 6,810 divided by 5 times 10 to the minus 3. And don't use 6,810, use the accurate one. Like on your calculator, keep the value as accurate as possible. Round it off to the appropriate significant figures only when you're writing the answer. So 6813.4.
It's 1362680.
1362
680.
680, right? And that's joules, right? So in kilojoules, it's going to be, I think, 1362, right? And then, TK. And you can round it off to 1360 kilojoules. TK, keep it till 3 significant figures. Now suggest, is that clear? You clear? Is everyone getting this answer, right?
Yes, sir.
Now suggest 2 reasons why the value.
I have a question. Will we be given the specific heat capacity जिस तरह ऊपर वाले question में?
नहीं, अब तो दी भी होगी, नहीं अब तो दी भी होगी, ये तो याद रख लो, it's going to be 4.18, ठीक है? But previously it was written in the data booklet somewhere. But now you're not going to have the data booklet, so it would be written in the question. I think somewhere at the start, yeah, 4.18, right?
Okay, sir. Thank you.
But now it's not given, okay? They suggest 2 reasons why the value of the combustion of ethanol determined by simple is likely to be lower than the true value. 2 reasons. Heat loss, right? In an actual experiment, there's going to be a lot of heat loss. So a lot of heat is actually getting wasted. So the heat you're measuring is actually lower. Is that clear?
Yes, sir.
What's the second reason? Why is the heat that you're measuring is lower? What's the second reason?
Some of the ethanol is left over in the.
So I mean, we can't be sure that the ethanol is burning completely. So if it doesn't burn completely, less heat would be produced, right? And you're going to measure less heat. Or maybe
And some of the heat will be absorbed by the crucible.
No, heat loss. No, that's heat loss to the surrounding.
Oh, okay.
So वो जो thermometer temperature rise कर रहा होगा ना, that would be lesser because a lot of heat is lost. So the heat that you'll be measuring would be lesser. या फिर वो ethanol is not burning completely. If it doesn't burn completely, the heat that is produced would be less, obviously. Or maybe the ethanol is impure. ठीक है? तो चल ठीक है, ये पे next time continue करते हैं, ठीक है? ये थोड़ा सा ही रह गया इसका. We'll try and finish this off as well. W16 QP23, ठीक है? चलिए, okay everyone.
Thank you, sir.
Take care, Allah Hafiz.